Volume. Volume. Testing, testing. 1, 2, 3. Testing, testing. Hello, hello, hello. All right. This is not going to be too horribly long. We'll get our technology to help us get us in the places we need to be. And really, in talking about correlation, I talked about the things that we needed to get this set up, which is the linear regression itself. When we did these scatter plots, we were trying to find a line that would best describe the data. And that line is what we're going to find here. Now, one of the things you will see, nope, that's still not doing its job. Had some problems with this earlier. Let's see if I can get it back to where it is. There we go, good. Make sure everything's working in the right places. Yeah, good, all right. Sorry about that. A little bit of unprediction there. The type of line we were looking at, we were talking about a linear equation having y equals mx plus b, where m was the slope, there we go, slope, and b was a y-intercept. So if I were to graph the thing, b, that's the value of b. However far up the y-axis is, that's b. And then the slope tells me how steep the line is, how much it changes in y over its change in x. So the slope is change in y over change in x. And that gives us a way. And with this equation, if I know a particular x value, I can plug it into here, or the line tells me what the y value would be. So if we can find a line that our data is kind of centered around, we can make future predictions. And I did that with the regression lines. We're going to want to do it a little more formally in regression. Now, one of the things I'm going to warn is our technology. We'll call this A and this B. So most of the literature talks about this as being M, and the technology is going to, the calculators are going to call this A and this B. I'm not 100% certain why the slope was called M in the past. It's one of those traditions that gets carried on, just like X stands for the unknown thing because of a translational error. So the first thing we do is we find that R value, that correlation coefficient. And the correlation coefficient, if it's significantly close to 1, positive or negative 1, it's significantly close to 1, and far away from 0, then we're going to say that there is a correlation, and we can use the line to predict the model of our data. And so that line's called a regression line. We regress the data back to the line, and we can predict future values if we know the equation of the line. And so each data point has a predicted value and an observed value. There's a distance separating it. And then we call this residuals. You hear people talk about the residuals or how far off you are. And so the predicted value, so let me just see if I can get, yeah, pen's working again, good. D3 here, showing, oh wait, didn't switch over, go back. All right, good, there we go. So we take our correlation coefficient, we verify that it is close to 1, and we get a regression line. Good, things are switching again. And that regression line we use to predict future values. Now that line will have an equation. This will have some y equals, and again, matching our technology, ax plus b. If I know a particular x value, I plot it in and it tells me it should be there. But the original data, right, doesn't match nicely to the line. Right? The line's the best fit. It's not the exact fit, it's the best fit. And so there's little differences here. And they're the things called the residuals. And here's a graph of the residuals. And so this distance is the observed value from the predicted value. The observed value from the predicted value. And it's called residuals. It kind of goes back into the thing that in statistics, right, or in any real-based thing, if we have some formula that predicts things, some line that we can make a prediction out of, reality is going to have random errors, random things that drive it out, problems in our measurements, problems in the systems running perfectly. There is no perfection in this. And so we have random error. And that random error drops things on either side. And those are the residuals. And they can be positive or negative. But all the residuals should cancel out. And so if you square the residuals, you're looking for it to be at a minimum. And we call that the line of best fit. What this is saying is that we're looking for the line that is the smallest distance away from each point. If we want to think of it as a way of doing points. And so that's where this nasty equation comes into play. This is very similar to the R calculation, and it is adding up residuals, and it's finding their distance from all the possible lines it could make. And so you can find the slope by taking the number of lines and multiplying their xy's, and then subtracting from that the sum of the xy's multiplied by themselves. And you do the same with the x squared. And so you end up with the difference in y's over the difference in x's. And this y part keeps track of the residuals. And you can find the equation of the line where it intercepts the b-axis by taking your average y value minus your slope that you figured times your average x value. And that turns into this, your average y value minus your average x value. And so we're really averaging all the possible lines that you could put together with the data and finding the one and all the possible lines in the middle of them. By doing the averages of all the possible lines and all the possible lines in the middle, we find all the things in between them, and we find the one that is closest to them. Again, I'm not going to fight back and forth with doing this by hand, but we're going to look at it for technology. Now, this is the regression line that we did when we did our R values the other day. I'm going to do this in the calculator. I have put a video on the TI-30 with this data up. It's at an angle. I'll try to fix the angle on it coming through. That was a camera change. What I want to do here is we're just going to use our technology to enter this data. So this is on the slides. I would try to have the data nearby. I'm going to switch over to the calculator now, though. Okay. So what I want to do is I want to come into stats, and I want to put my x values into L1. And so my first x value is 1.8, then 1.3, then 2.4, then 1.5, then 3.9, then 2.1, then 0.9, then 1.4, then 3.0. I'm just reading down the list. Sorry. I'll get my monotone voice on. And 4.6. And so there are my 10 entries for L1. And come over to L2. Now, the important thing is they have to match. 1.8, 604.4. And so I have to make sure that I match my L2 value with its corresponding x value. Otherwise, I don't get a good data pair of points, and this doesn't quite work out because of how the points don't match up. 54.0, 3. So if you have the list, bear with me as I enter them all in. 370.4, 742.3. 7.4, 742, 2.1, 340.5, 232.0, 262.3, 441.9, and then the big end point 1157.7. And I now have my data in. So I have created my data. Now, this is something the TI-84s exclusive to them. That's odd. If I want to come back and I want to go to second and catalog, I want to make sure that I have diagnostics on. It will not display R values unless diagnostics is on. Now, I'll hit enter there. Enter, and we're good. So now I'll come into stats. I'll calculate linear regression. AX plus B. My X values are list 1, and my Y values are list 2. And I'll come down to calculate. And it gives me the A value, which is the slope of my line. Gives me the B intercept, and it gives me my R value. So I can look at this and go, 87%, an 8.87 correlation coefficient. It's close to 1. This line should be predictable. It should be used to make predictions. And so this is how we do it on the TI-84. On the spreadsheets, if you look at the PDF I sent you on The Real World is Messy, you make a column for your X data, you make a column for your Y data, and you can choose something called a scatter plot with the two columns. Inside the graph for a scatter plot, there's an option show line of regression, and it will immediately calculate these values on the scatter plot. I might work on a video for those, but I do have that PDF that I sent for the people using Excel. I put up a video on the TI-30 that shows you how to get these values out of the TI-30 XIIS. It's the only calculators I have to demo. I have a TI-89 here, but I haven't seen anyone else use them. I should say I have a TI-89 Titanium. The original mode TI-89 is slightly different. But if you are having a problem with your particular calculation and getting through these, let me know what technology you're using for it, and I can try to help. All right, so we have our R value. Our R value says it's significant, and we have our A, which is about 256. So we're able to make a predictable value out of this. And the predictable value we get is we get this line here. We take our A value and our B value, and we can make an equation for the line. So we can predict more precisely I remember yesterday I was pointing to the graph, or yesterday, Monday, I was pointing to the graph saying if a country was somewhere in here, we would expect to see that its CO2 output, if its GDP was 3.5, we would expect to see a CO2 output that would be relevant to it. And now we have an equation where we can use that to predict. And so we sketch this line, and we have our GDP in trillions of dollars. Well, we have an equation for it. And they're saying note it passes through one of the points, one of the data points. And so here, all right, I'm going to have our linear regression line. I want to do the prediction on it. Give me 2 seconds here. There it is. All right, so I knew this question was here. I wanted to follow up with the CO2 chart. I just forgot they did the mini tab thing in there on these slides. So the regression equation for the gross domestic product ends up being this y equals y bar equals 199.535 x plus 56.03. So y prime equals 199.535 x plus 56.036. All right, let's see if this works now. All right, and so there's our equation. We're going to be able to use this. We're going to be able to use this equation to make predictions. And there's two ways I can predict with any formula. I can look at my output, right? And I can look at my output values and see what I can get from my output. And so in that case, our output is metric tons of CO2, right? So I have my metric tons of CO2. So I think I'll do it over here. Y bar, the units are metric tons. And X is GDP in trillions of dollars. Okay. And that's what we have. So, this is a significant linear correlation. I can make a prediction. I can say, hey, you know what? If I have 1.2 trillion dollar GDP, what is the consequence of my energy cost for doing this, right? How many metric tons of CO2 does making this amount of money produce? Since burning things is the fuel of economies, the consequence of making this much money is an output in CO2. And the linear equation tells us, hey, there might be a correlation between them. And so we can use that to plug in to our equation. So we go, hey, I'm going to have y bar. I want to change colors here. Bear with me. Y hat. I guess that's a hat. So y hat 1.99.535 times 1.2, because we're making $1.2 trillion. And of course we'd run over to the calculator and put that through, because what is it? That's 305-ish. Let's see here. Put all that in. 199.535 times 1.2 plus 56.036, and we get 295.478 metric tons of CO2. And so if this correlation is true, if that R constant that we calculated first, which was positive 0.87, is close to 1. When we say close to 1, I tend to 70% or more, 0.7 or more. Then we calculate the linear coefficient using either our spreadsheet, our calculator, or going long form with the equation, adding up the sums of the y columns and the y squared columns. But we get an equation of a line, and this line predicts what value should be. So if my country is making 1.2 trillion GDP, then the effect of that, the fuel burning to do that, is 295 metric tons of CO2. There's some neat things too in this prediction. Is if my GDP is 0, I'm still producing 56 metric tons of CO2. So there's a production of existence without having a gross domestic product. There's some existence cost in there, which is a neat thing to say. The things that come across. All right. Well, let's look at this in another aspect. We could try to make a particular carbon target. And so what would be the cost without changing energy production of a carbon target? And in a way, this is the argument amongst climate change, is the cost of changing the infrastructure can affect the GDP until the infrastructure is switched over. So if you have a particular carbon target, and we'll say that our carbon target is 400 million metric tons. Right, these are millions of metric tons, my bad on that, forgetting the millions in it. Alright, we're not going to produce any more waste than that. Well, what is going to be the limiting factor of that to our GDP? So we put that in for Y. And now we want to solve for the X. We'll want to find the GDP. So we'll subtract 56.036 for each side. And then we'll divide by 195.535. And that'll leave me with X on its own. And I'll go back to my calculator here. So 400 minus 56.036 divided by 199.535, and we get 1.7 trillion. And so the GDP is $1.7 trillion. So you can have this limit, it will change where your GDP outcome on. This is all given the current system. All of this data is observed from the current system. And so there's a strong correlation between the amount of money your nation produces and the amount of carbon dioxide that you need to fuel the economy, literally, quite literally. And so until infrastructures change, this correlation is fairly strong. So any ask to drop down carbon emissions has a GDP limiting effect. Now, the argument is that we want to break the correlation, right? And that's done by, instead of losing GDP, we invest the difference short term to change the fuel type to break the correlation, to make this correlation not strong, so that we fuel our economies with things that don't produce metric tons of CO2. In theory, right? But at least this is what the data is telling us. If we look at the data, the country's GDP is very closely related to the amount of stuff it burns, and the stuff it burns kicks out CO2. All right, and so we looked at the different ways we can use these as predictive values. And so they become predictive values. And so linear regression, let me close that. It's back to the front. Get back over here. I think I'll use this camera a little bit more. Sorry about the camera bit here. So linear regression is a tool to take many data points and see if one input value, exploratory value, is affecting the response value. And so we look at how the two work together, and we see if they're correlated. If they're correlated, we can generate an equation. Let's see if I can do this right. See, I see myself over there, and it kind of lets me know if I'm like in view because the way the cameras are, kind of head chopped off. So I need to make sure I'm seeing the board, and there's kind of like a dead spot on the bottom of the board I'm trying to fix. I just got the camera this weekend, trying to make it all work. Luckily, this morning my computer updated a video driver, and none of the Blackboard stuff was working, so I had to do this for my morning class with this. And for the things I'm doing right now, I don't know, that pen on tablet's been killing my hand, so I'm doing this. Unfortunately, well, pardon me, quarantine hair and beard, and I need a shower. But shh, don't tell anyone. It's not like this is going to live on YouTube for a while. All right, so let's do this with another set of data here, and see if we can see anything more for it. Yeah, I want to look at a data. I want to put a data set up here. We're going to graph it. We're going to go through the whole. Oh, I'm sorry. We're going to go through the whole gambit. I'm going to put up some data. We're going to take the data, and we're going to put it in our calculator. And well, first we're going to do a scatter plot of it, and then we're going to put it in our calculator. We're going to see if there's a correlation value, and then we're going to put a linear model from it and make some predictions. We'll do the whole gambit of things. I think that I want this one. Let me see. Is this the right one? A79, A79, 67, 79. I think this is the one I want. Yeah, that does what I want. All right. So let's get. I'll write my data in white, and I think we'll do our. Alright, so I'm going to put it up here. My x values will be hours studying. Will be x, and my hopeful output will be test results, test scores for y's. Anyway, the more I study, do I get better test scores? And so our data is, let me just write down the data so that you don't have to keep looking at my back. Peek to see if it's all fitting. Yeah. I still have that slant to my writing. Yeah. The 8 fit? Yes, good. Alright, I want to join my data points together. Just so they're pairs of data points. Alright, there we go. So we have some data points. That worked out much better than I expected. I didn't knock anything over. Alright, so I want to graph this in a scatter plot with x and y values. So There's my y-axis. And this will be my x-axis. And so this is my test scores. And this is my hours studying. So I'm going to use blue for each data point, but I have 0 through 8, so one, 2, 3, 4, 5, 6, 7, 8. I think. Oh, wait, I messed up already. Good. Counting by halves. 2, let's see, so 1 skip, 2, 3 skip. Good. This is 4, 5, 6, 7, 8. So there's my studying by hours, and then now I need to trying to use the width of the chalk to measure a bit. Not doing a great job with it, but not doing too horrible. The hardest part with graphing, right? Remember I have the graph blackboard in the classroom to do this. We do have graphing paper that will help. All right, so let's see. We're going from 40, so this is 0 to 100. 20, 40, 60, 80, 100. That'll be our graph. So all our graph will be within here. And so our first piece of data was I didn't study at all, and I got a 40. I studied 2 hours, and I got a 51. So let's see, 50's there, 2, 51-ish. I studied 4 hours, and I got a 64. There. I studied 5 hours, and I got a 69. I studied 5 hours, and I got a 73. I studied 5 hours and got a 75. I studied 6 hours and got a 93. Right about, whoops, that's my 100, that's why. Right about there. And I studied 7 hours, got a 90. And I studied 8 hours and got a 95. So all said and done, we can see there's a general trend this way. And so I'm gonna make the prediction that with this data there is a correlation between the amount of time you study and your test score. So we're gonna put this data into the calculator, we're gonna get our R value, and of our R and the equation of our line. All right, so there's my calculator. And what I'm going to want to do is I'm going to go to Stat. I'm going to keep my other lists. So what I'm going to do now are my X values are going to be L3. So my first X value is 0, then 2, then 4, then 5, 5 again, and 5 again. I have 3 5s. 1, 2, 3 5s. Then a 6, a 7, and an 8. So those are my X values. My L4 is going to be my Y values. And the person who studied 0 hours got a 40. The person who studied 2 hours got a 51. The person who studied 4 hours got a 64. And for 5 hours, we had a 69, a 73, and a 75. 6 hours was a 93. 7 hours was a 90. And 8 hours was a 95. So we have all of those in there. So we'll go to Stat, Calc, and we'll do our linear regression. And now I want to change my lists. L3 is my X values, and L4 are my Y values. And that's a very strong regression. We have an R value of 0.968, and we have an A of 7.45 and a B of 37. So let's do this here. Let's put these values in. So our R value is an R of 0.9684. 56, right? And so this is close to 1. It's positive because this has a positive slope. And being close to 1, we'd say it's strongly correlated. Now, the equation of the line it's telling us is that my slope is 7.4513 times x plus, for my b value, 37.44.440. Oh no, 10 like that. 37.4410. And so we have a predictive value. And so you can do really, really silly things now with once you have a correlation. You can say, well, what happens if I study for 10 hours? Well, for 10 hours, this becomes 74. And 74 plus 37 is, hey, you should get 100. So there's obviously, this probably isn't linear for all domains. Infinite studying does not turn into an infinite grade. But you can use this idea if you have the data for the correlation, right? You can always collect data on yourself, on your peers, is that, well, if I studied for 7.5 hours, so I'll run over to my calculator, and I want to put 7.5 hours in. I get 7.4513 times 7.5 plus 37.4410, and you should get a 93. So you come to 7.5 up here, and you're somewhere around 93 on the line. You can also do the other thing. What is the minimum amount? What minimum amount of time should I use? Weird. This just orientation's weird. Hello. To get an 80. Let's say 80. You know, I just need an 80. So you can go, well, if I want y to be 80, then I subtract from it the 37.4410. And I divide the whole thing by the 7.4513. And that will tell me, hey, how many hours can I work in there? So 80 minus 37.4410. And I divide that answer by 7.4513, and it says, you know, I'm going to need about 5.7 hours to earn an 80. And if we look at our data, 5.7 hours, yeah, 80 somewhere in there. And so this is what correlation lets us do. It lets us determine how strongly, the R value is how strongly our data points match a line. And the closer this is to 1, positive or negative, the more strongly correlated it is. Then we can figure out the equation of the line that all of our data is near. Our data is acting like a line, and lines can let us predict something. I can know one of these values and predict the other. All right, that's it. That's the whole book. No, it's not the whole book. It's everything in the book that I wanted to cover. Linear regressions, R values, hypothesis testing, and confidence intervals are really the key things we tried to build up. Look, it's just my shoulder. It's the key things we tried to build up. I swear this was higher yesterday. I must have. Oh, that's right. When I went to film the TI-30, I had to lower the camera and move things around. So now I have to do this. We'll just go like this. So we've hit our key subjects, right? Confidence intervals tells us how sure we should be about data groupings, what we can do with error and when we measure things. So that's important, knowing how confident we are in data. Hypothesis testing lets us know how to make a decision with data. Again, if we start with what I said this whole thing was, statistics is the science of studying our measurements and how we can make predictions from it. It is the science of here's what reality tells us, how confident are we of what reality is telling us. And again, philosophically, I very much of the opinion you can't prove anything. You have to assume. The assumptions I make is there is a reality. Right? It doesn't have to be. This could all be a crazy mad dream. But I don't think it is. I think there is a reality, and that reality is external to me. It follows laws that are observable and predictable. Statistics is the job of saying, okay, we have this reality thing. What does it mean to be observable? And then how sure can we be of what we observed and what our observations predict? And so we use the really the only tool we have for doing that, which is numbers. Because we can compare numbers, big number, little number, different number, other numbers, right? We can compare those things. And so that's what we did. We started out by how do we observe? How do we gather data and collect it together? And that was observational statistics. It's our frequency charts and our original histograms. We took a little break and I said, you know what? If reality has some truth to it, when we observe it, there's going to be randomness in our measure and our error. So we studied what randomness would look like. We studied probability and we studied probability distributions. And what we were hoping to do was, well, if we're measuring things in a random fashion, just grabbing data as we could, then that randomness would appear in the numbers. And so that's why we studied the randomness. And the main random distribution that we use is going to be the normal distribution. Because normal distribution says there is some truth, some true value that reality has. When I go to measure it, I'll sometimes be on, sometimes be off. And it will fill out in a normal curve. Because the randomness should be equal of being I measure too big or I measure too little. It also says that if there is some law in the universe that drives things, right, the input values into that law will sometimes be off and hopefully giving random results. Now, as we'll find, as we'll find, this normal curve appears everywhere because of that. There is a true value that represents kind of how a system works. But the system itself has weaknesses and strengths that, if they're randomly distributed, make it normal. And so normal curves pop up everywhere, and that was chapter 5. And that becomes our Z-scores. And they become the main determining thing, the area under this curve, these normalized curves. And so there we took all the observations and statistics and we used randomness on it. And then chapter 6, 7, and this chapter is talking about the predictive power and what we can infer from chapter 6. We said if I'm going to make a claim, how confident am I of that claim? or I should say, if this represents the real true value, then if I want to be 90% confident of it, I'm going to have some confidence interval, right? That has a range of it. And so that's what Chapter 6 did. And we talked about it. Do you know how the population is spread? If you do, you can use a Z table. If you don't, you have to use your sample, and you have to use a T table to find our confidence interval. And we could say we're 90% certain that the true value lies within this range. We're 95% certain the true value lies within this range. The confidence level determined the width. And we can also look at the error that we're allowed to get in taking our samples. So that was all of chapter 6. Chapter 7 said, I want to make a claim. I want to say this is the true value. And so we had to do hypothesis testing, where we make a null hypothesis and its alternative, where this had equal, greater than equal to, or less than equal to. It had some equality, and this ended up picking up the unequal part of it, its complement. And by doing that, we're able to say, well, if I make a claim, there's going to be errors, and those errors are going to be random, so they'll make a normal curve. And so we did our tail testing based off of that. Notice how this idea of randomness worked on pushing everything through. And then we come into section 9, where we talk about how one variable, how we can tell if changing one thing affects another thing with correlation. And that works us through. These are the main tools of statistics, and you should see them used. All right, so Bill put a big thing about Monday. Monday would have been test day, right? Now what I'm going to do on Monday, since it is the last day of classes and when things are due, is I'm still working on like email, video responses to the questions people have on different problems. I will work out problems people have that I haven't responded or already put up online in this time, and I'll be open to questions. You still have the time on Monday to do things. It normally would have been sit in the class and sweat while I give out an exam. I will use that time to review any problems anyone has. The exams are up on Pearson, so just throw questions at me. All right, I'm gonna go walk towards the camera and then away.